from sort of left to right. You go progressively across the ribbon bar. So apologies if you can hear some... There's apparently a pack of angry birds outside who've just heard that I'm recording and have decided to go mental, as it always is. I refuse to start this again just because some angry birds are kicking off in the background, right? Enough's enough. Here we go! Nope, the birds were way too much. Had to start again. So welcome back to my most underestimated video series that I've ever started. Oh my god, have I underestimated how many buttons there are to cover here. But all buttons in Autodesk Inventor, mate. We're still in part mode, 3D model tab. We've done all the buttons up until stress analysis, which unfortunately there's more than one button. When you click this, it does jump off into a different set of ribbon bars, so we have to cover all the buttons in there. As always, it's not a tutorial, it's not a guide. It's just a, oh, what does this button do? Oh, okay, move on to the next one. I am not a simulation expert. If you are looking for a full tutorial on simulation, there'll be other people far more suited to this. My explanations are probably not going to be the best, but hopefully I can give you a rough idea as to what each button does, and that's about it. It's not a guide. Right, let's go into simulation. And we're going to start with creating a study. And Inventor's simulation is unofficially, I suppose, meant to be just like a first pass. Autodesk do have high-level simulation packages, the likes of Nastran and other third-party packages are available. But as a first pass, just getting a rough idea of how something behaves under forces, it's all right. So we've got different types of design objectives that we can run in Inventor, including Shape Generator, which is the generative design style of simulation, removing material and retaining strength, that kind of thing. But we're going to be working with a Parametric Dimension style design objective. Now, the whole point of Parametric Dimension, again, they could have named this better, but Parametric Dimension allows you to take a parameter or multiple parameters in your model and then run the simulation with that parameter at different values. Typical example would be thickness. Say this is 3 mil thick. You can say to Inventor, run a simulation, the same one, but let's do it as if the thickness was 2, 3, 4, and 5 mil thick, and it'll show you the results at all those different thicknesses. And then you can say, oh, actually, it was fine at 2 mil. Let's go with that, and you can promote that model into the original design, and then save some money and weight, mate. Wait, mate. What am I doing? Right, anyway, so let's crack on with the parametric design study. First button is indeed parametric table. Right, cards on the table here, mate. Autodesk could have done a much better job of this. This had me mind blown for a long time. I was right clicking all over the place going, why is nothing happening? I don't understand what it's expecting of me. And it turns out what you've got to do is you've got to select this. There may be another way of doing this. This is the way I found. You have to select this node. Once you've selected it, when you right click, you get show parameters appearing here. That's what it's expecting. Out of all of this up here means nothing. You need to pick this here. But plot twist, if you don't have that selected and right click, it's not there anymore. It's like, who thought this was a good idea? Anyway, let's not dwell on that. Right, so you've got to click that, right click, show parameters, and it lists all the parameters in your 3D part. And we can go with the thickness. That's what we're going to vary across the parametric study. So I'm going to run simulation as if this part has a different thickness. So tick thickness, click OK, and it adds that into the parameters. I think you can add more than one, but the more complex the simulation, the longer it'll take. You know, yada yada yada, usual stuff. So right, the parameter name's thickness. The value is currently 3 mil. That's what the thickness parameter is currently at. Now you can say to Inventor, run it at a range. So we can say, I want you to run a simulation at 2-5. So it's going to run a simulation at between 2 to 5 mil thick. Press return. And then for some reason, I don't know why, it defaults to 3 variants, which is 2 mil thick, 3 mil thick, and 5 mil thick. Where's 4 gone? Who knows? No idea. If you want to run it at 4 mil thick as well, you've this number here, right, :3, is the number of iterations within the range. So 2, 3, and 5. Why it's defaulted to that, no idea. Change that to 4 and press return. It's now got 2, 3, 4, and 5. Right. And then what you do is right click again, and then you generate all configurations, and it'll give you a visual preview of what it looks like at 5 mil, 4 mil, 3 mil, and 2 mil. There you go. All right, so that's all the the variations generated, is what I'm trying to say. We can close that down. We've now got 4 different simulations that are going to run when we click the Go button. Next button is the material. Right, in material, it by default goes to the material that you applied as you were modeling it, which is fine in most cases. But if you do want to go, I want to see what it comes out like running it at just normal, good old general stainless steel, you can override that in here, and it'll not use the original material, which is good, I guess. You could probably somehow, I haven't figured it out yet, but you could probably vary the material in the parametric study. What happens when I use plastic and stainless steel and rubber and plasticine and blue tack and Play-Doh or whatever else you want to go with. You could probably do that. Right, next panel is prepare. Alright, this one here is all about finding thin bodies. This is where my knowledge of FEA kind of dwindles a little bit, because I know why, I know what it's doing, but I don't really understand why it's doing it. It's all about thin models. An inventor performs an equation. It does a formula to detect whether or not your model is too thin to run a simulation the way it is now as a solid model. And that formula is L over D. It's the L over D ratio, right? So let's bring up a calculator. Preparation is key here, Neil. Right, let's calculator. So L over D, L being the overall average length of the model. So let's say the overall length is roughly 500 mil. D is the thickness. So you go length divided by the average thickness. So say the average thickness is, I don't know, 1.5 mil. The magic number is 100. If this comes out at greater than 100, the model is considered a thin body, and it's 333.3 recurring. This would be considered a thin body. Inventor would then recommend that you convert the solid model into a surface shell, or a thin surface, and run the simulation on that instead of the solid model. I think the reason for that is, let's change this into an actual thin body. So we'll convert the actual thickness to 0.1. So this would be considered a thin body. I think the reason is that when it meshes the model, the mesh elements would be too thin for Inventor to accurately perform a simulation on it. So it goes, I don't trust what the results would be. Let's convert this into a thin surface and the results will be a bit better. And all you need to do is just go find thin bodies, and Inventor performs that equation for you. So you'd say find thin bodies, and it goes, well, actually, now that you've turned this into 0.1, this is a thin body. Do you want to generate the surface? You click OK, and then off you trot with a thin surface. And that's pretty much it. It will perform the analysis on that surface instead of the solid model. Let's put this back to what it was, which was 3 mil, right? If you, for whatever reason, that absolute mystery to me, want to convert surfaces anyway, if it's not a thin body, you can do it yourself with mid-surface and offset. Again, there'll be FEA experts out there, analysis experts that'll go, oh, actually, there are genuine reasons for doing this, and by all means, tell people in the comments why you would do that, because I have no idea. But you can say generate a mid-surface, pick the solid body, and then click OK, and it'll generate the mid-surface for you without it even being an actual thin body. And then you've got offset. Offset, again, a complete mystery to me. It'll offset a thin body a distance away from the original model. God knows why, but you can do that. You can say, right, that's the solid model. Offset a surface by 10 mil, and it'll go ahead and do that. That's now offset 10 mil away from the solid model. That's what the buttons do. I never said it was a tutorial, mate. That's what the buttons do. Moving on to the next. Right, constraints. Most people with an interest in simulation will understand the constraints. They're pretty standard across all simulation packages, the same with the loads. So you've got a fixed constraint, you apply that against a face, and it's like when you apply a load to a model, act as if this face here is fixed and won't move. That's what a fixed constraint will do. And I guess for something like this, these faces here would be fixed, and these faces here would be fixed. They'd be like welded to an upright or something like that. But that's too many clicks. Right, okay, so that's a fixed constraint. Then you've got a pin, which restricts movement in the... Well, it restricts movement up and down. You would usually apply that to a cylindrical face, so that face can spin, or the body can spin, but it can't move up and down. That would be a pin constraint. A frictionless constraint means that this face here is free to slide normal to the plane the face is on, but it can't move up or down when a force is applied. Right, loads. We've got force load. You pick a face, and it will apply a force load evenly across that entire face. If you just want to apply a force load to a specific region on that face, you have to use the surface tools to split the face. But then you can just put a force load, say, of 2,000 newtons. Click OK, and there we've got 2,000 newtons pressing against that face, evenly spread over the whole face. That's important to know. It's not a pinpoint load on that little dot there. No, it's 2,000 newtons that I type in, evenly spread over that face, pushing against it. And we've got pressure, a pressure load, same again. You can do automatic face chain with this, so you can, if a face is joined to another face, it'll spread the pressure load across all those faces. But same again, pick the face, apply the magnitude of megapascals. Let's go 1,000 megapascals, and then okay. All right, bearing load. We've got moment load, turning load, gravity. Gravity is gravity. I mean, you pick an axis, you pick an edge, and then you can specify the direction of gravity. I don't really know how much difference gravity is going to make to something like this, to a thick metal plate. I think gravity is going to have too much of it. It might have, who knows. I'm not an FEA expert, but gravity might make some minuscule difference that tips it over the edge, who knows. Right, then we've got remote force. Remote force is the same as a normal force, but rather than a normal force, which acts as if there's something touching the face and applying the force directly against the face, this acts as if the force is coming from above or inside the component. So you could say apply a remote force to this face here of, say, 500 newtons, for example, but then act as if the force is coming from, say, 20 mil above it, for example. And then that's where the force is coming from. All right, and then you've got body load. A body load is, well, gravity is a body load. It's a load that's applied to the entire body rather than just a single face, and that can be it could be linear acceleration or it can be angular velocity. So those are your different loads. We've got contacts. Contacts are only applicable to assemblies. You can't use contacts in a single part, but contacts dictates to Inventor how two parts touch each other. If we were to say automatic contacts, there's nothing it can do, so nothing happens because there's no parts with contact here. But if we go into manual contacts, we've got different types of contacts. So are the two parts that touch each other, are they bonded together? Are they separated? Do they slide together? Like that would be like the frictionless constraint. Do the parts slide but don't separate? That kind of thing. So you would have to apply these contacts between parts. So when a force is applied to one part, how does that part then impact on another part? So those are your different contacts. You just pick one part, pick the second part, and then it'll apply the contact. The best way to do that, though, is to use automatic contacts. That works off of the constraints you've applied at assembly level. So if you've applied a mate constraint between two parts, the automatic contact will look at the mate constraint and base the contact type off of the type of constraint you've applied. Right, we've got mesh, right? This is where we're getting into the nitty-gritty of it, mate. Right, mesh, this will just mesh the view using the default settings, right? We'll go for this last. Before you mesh the view, you don't have to. It depends how accurate you want to be with this, but you can go into the mesh settings and you can refine how fine you want the mesh to be. So the average element size is 0.1 is a fraction of the overall bounding box length. So Inventor puts a pretendy box around the whole part, and each element will be 0.1 of that overall box size, which is quite big. That's quite a big mesh element, but it just means that the simulation is going to be quite quick and also not massively accurate. And then the minimum element size is a fraction of the average size. So you can just play around with these, trial and error, get the overall elements that you want to get at. What most people do, though, is they'll refine the mesh locally on a face. So like if you know there's not going to be much stress on this face, you know the force is being applied against this face, so all the stress is going to be maybe down here, for example, then you can leave the mesh chunks big here and then refine them here so you can be really precise on where the forces are. This button here is the local mesh control. This is where you actually do that local refining of the mesh, but we'll do that after we've actually applied the mesh. So we'll click mesh view. That then breaks it all up into chunks. You can see the chunks are quite big, and if we know just from experience that the most of the stress is going to be around here, this is where we can apply the local mesh refinement. So then we can go to local mesh control. We can pick the face that we want to make the elements smaller, and then you can type in a value of millimeters as to how big you want the average element size to be. You've got, I mean, visually I've got no references here, so I don't know what size to go with. Let's just go for 2 mil. I don't know, is that going to be too small or too big? I don't know. Right click, update the mesh. And yeah, okay, that's fine. Okay, so that makes these areas here much smaller. And then you would probably want to do that for this face here and probably all of these faces actually. It would be good if it would chain the edges actually, but clearly it doesn't. And I think I'd want to refine the mesh there, 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 and there as well. I'm struggling to understand why this is not slicker than it currently is, but nevertheless, it is what it is. Right, average element size of 2 mil. Right click, update the mesh, and that'll make all of these areas an average of 2 mil. So yeah, all that means is that these areas here will have more accurate results than over here where we might not have as much stress. We probably will based on the pressure and the force loads, but that's what that does. Right, then we've got the convergence settings. The convergence settings is the number of H refinements. It's how many iterations of the simulation it does as it converges the results based off of a percentage value. So we can say put in, I don't know, 3 H refinements, the stop criteria being 5%, for example, and then click OK. And then that's it, mate. You click simulate, and then you click run, and it'll go ahead and perform all of our analyses, right? So it's what's it saying here? The deformation is large compared to the model size. So what it's saying is that I've applied a massive force, and the part is deforming quite significantly based off of the size of the model and the amount of forces. So I've probably applied way too much. So I'd be curious to see how much it is actually deforming. So we need to change this to the displacement. And wow, that's quite. So the actual, so based on what the. That's the actual deformation. I don't think it is. I don't think it is, mate. So yeah, I've put way too much force on that. Someone's probably watching this going, are you daft? Could you not tell how much newtonage you had applied there? You idiot. Yeah, okay, all right, fair enough. Right, so let's reduce the forces. So that one was 200 newtons. Maybe it was the pressure one of. Let's drop that down to 10. Gravity pressure, and the remote force. What was the remote force? That was 500 newtons. Let's drop that down to just 10 newtons. And let's update the results. Make sure it's not absolutely ridiculous. So yeah, Inventor was quite polite to us there. It was like, the deformation is a little bit oh, it's still quite large. Okay, I don't know what I've done here to make. Maybe it's the parts that small. I don't know. What's the displacement coming up as now? 61 mil. That's not too bad. So that's pretty all right. So based off of the newtonage we've applied to that face, there's the actual deformation. And there's your results on the left-hand side. So you got your von Mises stress, you got your principal stress, displacement, and safety factor, which is 0.04. Essentially, this part is going to break. It's going to break like a cracker. So, but anyway, it's done its job. All right, so that's the solve button. Then we've got various different buttons here which will allow us to investigate the results. So the first one is animate. So this will animate the displacement as the forces are being applied, and you can just change the number of steps. So it's just animating as the forces are being applied, 10 steps with a normal speed. You can go slower if you want, and yeah, that's animating the results. That's good for showing your boss and for your design reviews. Let's look at what happens when we apply the forces. You can clearly see here what's happening as the forces are being applied. Blah 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 blah. Probe. Right, again, this quite rude. Probe. I'm going to grow up, Neil. Right, probe is it's allowing you to pick a point on the model and investigate the exact forces and stresses at a particular point on the model. So what I'm trying to, I'm sort of thinking at the same time here, how do I get this back to what it was? Oh, yeah, it's because it's gone actual, right, underformed, that's it. So yeah, probe, yeah, you pick a point on the model and it'll just call off a label and say at that point the von Mises stress is that megapascals. And then you can say, well, okay, well the stresses are most here. You can pick that, and then 5,970 megapascals of von Mises stress at that point. How fascinating, right? There's the convergence graph. That probably means something to somebody. Doesn't mean anything to me, but that's your convergence graph. Same scale. This locks in the simulation scale so that when you do another simulation, all the results are proportional to each other. Because obviously that scale bar there, it's based off of 0 all the way up to the maximum stress, whereas the next test that you do, the stress might be a fraction of what this is, and you might want to look at it based in proportion to another test that you've done. So that locks in the scale bar. The color bar, this allows you to just edit the color bar if you want to be that finicky about it. You can change the location of the color bar and put it across the top if you want to. You can change the colors and all that kind of stuff. Again, it's not a tutorial, let's not go too far. Alright, the probe labels on or off. Alright, then we can show where the minimum force is, which we'll put a label where the absolute minimum amount of force is, which is up here. So clearly, as the force has been applied here, there's nothing being stressed at this point here. And then we've also got the maximum, which is there, quite useful. So that just pinpoints the minimum and maximum forces in the model. You can change the shading type. So we've got this sort of nice colourful gradient going on here where it blends the greens and the reds and the yellows all together. But if you don't want it to be that smooth, you can change the contour so it's just a little bit more, you know, visually hard on the eyes, so you can see more accurately where the stresses are, as opposed to it being a little bit more blurred out. Or you can have no shading for whatever reason. You can do that. Right, this is your FEA report. This was all well and good and great when ANSYS was kicking about, but you could generate the ANSYS report with the ANSYS badge on the top. But now that it's Inventor's FEA own engine, which was Plasitech, why do I remember that? Plasitech, whatever it was before Autodesk bought it. It's an Autodesk branded FEA report, which still holds a lot of weight with a lot of people. But yeah, you click OK and it'll go off and generate you an FEA report with all the results in. It's doing a screen print of all the results. It'll paste all the results into a document, which you can then do what you want with it. You can use that report in a project, or you can copy and paste the pictures out of it and use chunks from it. You can do whatever you want with it, mate. But that's your FEA report generated, and it looks a little something like that. All the results all into one, apparently, web page. Is there a save to a PDF button anywhere? Right click, you save as PDF, probably, yeah, you'll be able to figure that out. So it's put into a web page. Right, this button here is guide. Right, this is supposed to be an in-product tutorial for simulation. So I am new to FEA. Go easy on me, or I am familiar with FEA, but I want a bit of advice on certain aspects, and then it'll take you through. Maybe I should have done this before I started this video. But yeah, that's an in-product guide. And then finally, we've got the stress analysis settings. It allows you to alter some defaults to the FEA environment. Like, we went into the mesh settings before. The average element size is 0.1. If you find yourself constantly changing this to 0.2 or 0.05, you can default the settings in here. Same with the convergence and the simulation type. And there you go, mate. Wow, I'm not really all that confident that that was a very good video, but we got there in the end. I think it's probably enough. Oh, hang about, wait a minute. One thing I completely forgot is that we did the simulation as a parametric study with multiple different variants, didn't we? We put in like 2, 3, 4, 5 mil thick plate. Where's all those results? Right. You go back into parametric table, and then you can change the slider to, like, say 4 mil, and then if you watch the results in on the labels, you see the results will update. So the maximum stress when it's 4 mil thick is 3372, and up to 5 mil thick it drops down to 2154. So yeah, I completely forgot about that bit. Yeah, there's simulation, all buttons in Autodesk Inventor. What's next, mate? What's next? Convert to sheet metal. So yeah, we're probably going to be looking at sheet metal buttons next. That takes you off into the sheet metal environment with all the sheet metal buttons. So that's up next for you, mate. Hope you found that useful. If you did, press like, because people on YouTube crave likes and dislikes for validation. Thank you very much for watching, and I'll see you in the next video.